Hello, Steve. We are Team 31.
Yeah,
I'm Zvezdan.
Wenji.
Okay, and this is our computer. I will start going over the general architecture, the decoders, and the program counter, and the 32-bit adder, and then Wenji is going to go over the
LU and multiplexer and the display driver.
Yeah, sure. And then we're going to demonstrate you our two programs. So, first of all, this is a computer. I suppose you can see it. It's a nice computer. It doesn't do brainfuck, unfortunately, but I'm pretty sure we can do software accelerated brainfuck on it for the time being. But in the actual sense of things, everything starts with these three main memory modules. We've got the read-only instruction memory, we've got registers, and we've also got the RAM. And that's also parallelly connected to the display driver because we're using the harder map I/O. Okay. So in general, on a high-level sense of things, how things work is that we gather one instruction from the instruction memory indexed via the program counter, and then this instruction is decoded via the main decoder and the LU decoder, which basically turn on and turn off tons of flags around the system that can allow us to control different data paths. So that since this is hardware, all of the devices are functioning, all of the gates are having to have a specific value at some point. But with these flags, we're able to redirect the outputs we actually need to use. Great. So instruction memory, different flags, the turn on turn off the registers that can redirect the ALU, and they can do branching instructions, job instructions, adding, not adding, like storing memory, loading from memory, and
I will explain the multiplexer first. So from multiplexer is basically using the 1-bit multiplexer that it selects one input is the selector, like if it is 0, then the output will be A, and if it's 1, it will select the B, and then just combine it to 32 bits. And for the ALU, we need a 3-bit selector at F2 to 0, and F2 will first select whether the F0 will select whether the B is not or is like select B is not O is itself, and then output to add them together, or like A and B or A O B, and use the F1 and 0 to like 2-bit selector, so the output may be one of the 4 inputs in this one, and the 0 extent is from the A minus B. If the A is smaller than B, then A minus B will be a negative number. The first bit of the output will be 1. What else? And the display driver. It's like we need to use the comparator to compare the address, and if it is true and the writing enable is true, then the output will go into the enable register, which enable the register to record the data into it, and the output will be the same as the data if the clock is at the rising age, and then the 32-bit data, the last 24 bits will be output in the 7 segments on the hardware, and if the address is equal to the second one, then the last bit of the data will record to the switch, which, if the switch equals 1, whole 7 segment display will be switched off, and if it's 0, it won't lag. It won't make any effect on it. It will just display the data stored in the first address. Yeah, and the reset button will let the data result in the register B00 and displayed on the 7 segment.
So let's go with the multiply program. So first of all, we initialize our current number counter to 2. So we start building squares from 2. So this register is the current number that we're trying to square and then display. And in order to do a multiplication, we have to add this. We have to add the current number to a specific temporary variable n number of times. Of course, n being the same number as well. So we're counting how many times we've done this with this register, and we're storing the result of adding this number to itself multiple times in this register, which is what we're going to display as a result. And we're adding the actual number here in this loop, and we're incrementing the counter. So if we've added the number to itself enough times so that it's equal to the actual current number counter of T1, then we're going to break the loop. Otherwise, we're just going to keep adding. And lastly, we're going to display our temporary variable, which is the actual square, and then we are going to increment our main counter. And we don't have a reset statement because we're going to infinity and beyond. Let's put this let's put it into the ROM. So let's export it as a hexadecimal text. Let's type it into the temporary test file. Sure, go ahead. Let's open the terminal. Now we've got this test file which includes hexadecimal instructions, but we have to format it in a way so that we can paste it in the ROM file. So I've got this script that does this exactly. So I can do now I can directly paste it. Great. Congratulations, we've got a program. Here we've got the program running on the FPGA itself. Do keep in mind this is in hexadecimal. Yeah, now we're talking. Let's do it in slow motion 32 times.
Now I'm going to show the program I did to find the prime numbers in a range up to a number. And I first set the T1 to value 2 because a prime number starts from 2, and set T5 to the number we want to find the prime number in which range, and jump to display, and then display the set T4 to the value of T1 and display T4. Then jump to increment. In the increment, we increase T1 by 1 each time, and then check if T1 is equal to T5. If so, we initial T1 to 0, and we set T3 to the value of T1 and jump to loop. In loop, first we set the first value we want to be divided T2, and I use subtract and check if T3 is a negative number or 0. From this, we can know whether the remainder is 0 or not, and after T3 is small or equal than 0, it will jump to check loop, and it will check if T3 is 0. If T3 is 0, then T1 is not a prime number. It will jump to increment and check the next number, and if T3 is not 0, then we will add T2 to the next number to be divided, and if T2 is already equal to T1, then we will display the T1, because we can be sure that T1 is a prime number then, and again we will assign T1 the value of T1 to T3 and jump to check remainder, and in this way we can find the prime number. Now this is the prime number program on the FPGA, and it can count up to a number that we want, but it will get slower and slower as the number gets bigger and bigger.